Hello, everybody, and welcome to the Latin American webinar of physics. Today we have a very interesting talk. Is the webinar number 108 of this webinar cycle that we have. We started more or less in 2015, so we have a lot of webinars in the body, let's say. So this time it's gonna be a very interesting webinar because it's gonna be about the primordial black hole. The speaker is Julián Rey, that he is a PhD student at the Universidad Autónoma de Madrid in Spain. And basically he obtained a bachelor in Venezuela in the Universidad Simón Bolívar, and now is here in Madrid doing his PhD. So the title of his talk is Primordial Black Hole in a early matter-dominated era and stochastic inflation. Don't forget that you can see the webinars in our YouTube channel, and also to ask questions to Julian using the chat in the live transmission. Otherwise, you can make comment to the video once it's finished. So Julian, welcome to lawphysics, and you can start whenever you want.
Okay, can you see the screen?
Yes.
Yes. Okay. Cool. Thank you for the introduction, and thank you very much for having me. What I'm going to talk about today is the work that I've been doing for my PhD thesis, which is about primordial black holes. The talk is based on the 3 papers that you can see at the bottom of this slide, and at the end of the presentation, there's a full list of references. Let me start by saying that primordial black holes are very relevant dark matter candidates today. And what makes them interesting, in my opinion, is the fact that they do not require any physics beyond inflation. There is still a very large window of masses that remains viable, meaning that it remains unconstrained by experiments of about 5 orders of magnitude. The lower end in this mass range comes from Hawking radiation bounds, from bounds on the radiation that these black holes would produce if they evaporated. And the higher end on this mass range comes from microlensing experiments. Something else that makes these black holes very interesting is the fact that their astrophysical signatures, namely the fact that they produce gravitational waves and gravitational lensing, is something that could be probed within the next decade. What we want to do in this talk is we want to determine the effects that these 2 things would have on the abundance of black holes. The first one is the equation of state of the universe at the time at which the black holes form. Concretely, we're going to assume that they form either during a radiation era or during an early matter-dominated era. And the second thing we want to determine is the effect of the formalism of stochastic inflation on their abundance. And I will tell you more later about what the stochastic inflation actually is. We're going to explore these aspects in the context of 3 different inflationary models, 2 of which are numerical and 1 of which is analytical. So let me tell you a little bit about dark matter first. Any dark matter candidate we know should be dark, meaning it doesn't interact with electromagnetism. The second thing they should satisfy is that they should be weakly interacting, and the third is that they should be cold. And the black holes satisfy all these criteria. There are many ideas for what dark matter could be. For example, WIMPs, actions, sterile neutrinos, and machos. And by machos here, I mean neutron stars and brown dwarfs. And it's important to distinguish because people often lump primordial black holes together with these machos. But as I will show you in a moment, the primordial black holes that we're going to be considering are very, very, very small. And at least in comparison to these to neutron stars and brown dwarfs. So it's not exactly, they are compact objects, but it's not exactly right to lump them together. The oldest surviving dark matter candidates are actually these primordial black holes because they were first proposed in the 1970s. So let me tell you what they are. Primordial black holes are black holes that are formed in the early universe by some mechanism different to the usual stellar collapse. There are many ways that you can get primordial black holes, for instance, from the collapse of vacuum bubbles or from topological defects. But the way that we're going to get them today, the mechanism that we're interested in, is how to get them from a given model of inflation. This is a plot with the constraints on the abundance of the black holes. So here in the vertical axis, I'm plotting the fraction of the fraction of dark matter that could be in the form of primordial black holes. So this is a number between 0 and 1. And in the horizontal axis, I'm plotting the mass of the primordial black holes. So you see that on the left of the plot, there is a window that is still open, meaning that it is constrained by experiments. And on the below 10 to the minus 16 solar masses or so, there's you can see the constraints coming from this, the one that say e.g. gamma. These are the constraints coming from extragalactic gamma rays. And this is basically a constraint because we do not observe the radiation that black holes, very, very small black holes would produce if they evaporated. So we know that the black holes cannot be that small. And above 10 to the minus 11 solar masses, more or less, we have the microlensing constraints, and in between this window is completely unconstrained. But this is a region that could be probed within the next 10 years or so, either by femto lensing experiments or by gravitational wave interferometers like LISA. For comparison, I have also, on the right side, you can see a little tag that says LIGO, and this is where the masses of the black holes that LIGO has measured would be. So you can see that the black holes that we're considering are at least 10 orders of magnitude smaller than what LIGO has observed. So they're very, very small. So how do we get primordial black holes from inflation? If we want the black holes to form, what we need is to have very large density fluctuations at a scale that is comparable to the Hubble horizon. Yeah, so we define this number delta, which is we call the comoving density contrast, and this is the ratio between the density perturbation and the background energy density. And we're going to assume that these fluctuations are produced during inflation, as is usually done. We're also going to assume that transitions between different eras are instantaneous. So in this plot illustrates the situation. In the vertical axis, the function that I'm plotting here is the evolution of the Hubble parameter as a function of time, and the horizontal axis is time or temperature, however you want to see it. And we have plotted the different eras of the history of the universe. Yeah, on the far left, we have inflation. And then right after inflation ends, we have this EMD, which is an early matter-dominated era. Then after this is something that we're going to conjecture here. It's not something that has been observed or anything. Then after this early matter-dominated era, we have a radiation era. And after this radiation era, we have the standard matter-dominated era that occurs after a Big Bang nucleosynthesis. And then at the end, of the very right of the plot, we have this lambda-dominated era, which is the cosmological constant era that we live in today. So every density fluctuation, every energy density fluctuation has a certain scale associated to it, because we usually work with the Fourier transform, so it's better to think about the wave number. And what happens is that the scale leaves the horizon as inflation goes on. And by leaves the horizon, what I mean is that the scale associated to each fluctuation at some point is above the curve. So if you look at the black line that I have drawn here, the one that says log of 1 over k, you can see that the scale is, we say it's outside the horizon on the left of the plot where it is above the colored region. Then eventually the scale re-enters the horizon, which for this example, it happens during radiation domination. And it is only after the scale re-enters the horizon that it is going to induce the collapse. So the scale, the fluctuation is produced during inflation, and the scale associated to this fluctuation leaves the horizon. And once it re-enters the horizon, the fluctuation is going to tell the matter inside the horizon that it has to collapse into a black hole. So the collapse occurs long after inflation has ended. So how do we estimate the mass and the abundance of these black holes in a radiation era? Usually the assumption that we make is that the mass of the black holes is proportional to the energy density contained within a Hubble patch at the time at which the black holes form. So this is what is written in the first equation here. And we put a proportionality constant in front, which we call gamma. And because of causality, this gamma should be less than 1. because the energy density that collapses cannot be bigger than what is contained within the Hubble patch at that moment. And this gamma basically measures the efficiency of the process. Yeah, this is a constant that tells you how efficient the collapse is, basically. We know that this is from simulations. We know that this is about 0.2. And then if we play around with this equation a little bit, we find after a short calculation that the mass of the black holes is actually inversely proportional to the square of the scale associated to these fluctuations that is collapsing. So if you want to produce very small black holes, which what we want from the plot that I showed you earlier with the constraints, we know that the unconstrained masses are the small ones. And if we want to produce very, very small black holes, then we need the fluctuations that are collapsing to have a very large K. As the next thing that we can estimate is the abundance of these black holes. Yeah, or in other words, the fraction of dark matter that is in the form of black holes. And there's a number that is denoted by F, PBH, is the one that you can see on the last equation here. And the important thing here is that it's proportional to this function beta. Beta is a function that tells you how what proportion of the energy density is collapsing into black holes. And if you assume that the fluctuations are Gaussian, then this beta should be a Gaussian, basically. And you can think of it as going roughly as the exponential of 1 over the power spectrum of the fluctuations. So what's important here is that, well, let me tell you what the power spectrum is. The power spectrum is a quantity that tells us how these fluctuations are distributed across different scales. And this is actually a quantity that is computed from a model of inflation. You can, if you have a model of inflation, then you can compute the power spectrum. And this is actually measured by CMB experiments. So one might wonder if this is actually measured, well, is the value that we have measured by CMB experiments enough to produce enough primordial black holes to explain all of dark matter? And it turns out that it isn't. The value that we have measured for the power spectrum is about 10 to the minus 9 at CMB scales, but the one that we need to produce enough primordial black holes to explain all of the dark matter is of about 10 to the minus 2 or so. But this is not a problem because, as I told you before, the mass of these black holes is inversely proportional to the scale of the fluctuation. And you want since we want very small black holes, because these are the ones that are unconstrained, we want the scale of the fluctuation to be large. So in other words, we need the enhancement of the power spectrum to occur at scales which are much, much smaller than the ones that we observe at the CMB, meaning at a K that is much larger than the one that we observe. An example of the power spectrum is shown on the right-hand side. Before moving on to explain the plot, let me first say how we can get a large power spectrum from a given model of inflation. So in any model of inflation, the power spectrum is inversely proportional to the speed of the inflaton, at least in the slow roll approximation, which we actually need to break, but this is enough to understand the intuitive idea here. So the power spectrum is inversely proportional to the speed of the inflaton within a model of inflation. And then what you want to get a large power spectrum is for the inflaton to be very, very slow. So what we need to do is to have a feature, some kind of feature in the potential that is going to slow down the inflaton once it rolls down. For instance, an inflection point or a small hill. So the kind of potential that we're considering is shown on the left plot here. And you see that at very small field values on the left of the plot, we have the part that will correspond to the fluctuations that we observed at the CMB. And then later on, as scales are smaller and smaller, so for large K, we have an inflection point in the potential, which is the place at which the primordial black holes are going to be produced. And then at the end of the inflation, we have reheating, which is when inflation ends. So the power spectrum that will correspond to this potential is shown on the right side. And once again, you can see on the left side of this power spectrum, the value that we measured at the CMB, which is 10 to the minus 9. And then as eventually for large K, we have the peak that would correspond to this inflection point that you see on the left. The simplest model that we could consider is to obtain these primordial black holes is actually simply to put a scalar field and couple to gravity. So as you can see in this action, the model that we're going to consider now, this is one of the numerical models that I was telling you in the beginning, is simply to take a scalar field and couple it to the Ricci scalar in this way, via this term psi phi squared times r. And then what you do is you can actually get rid of this coupling by redefining the fields. So if you take this action and you redefine the metric and you redefine the inflaton field, then you can get rid of the coupling to R, which is what I show on the action that is at the bottom of the page. And the price that you pay for getting rid of this coupling, which you see is no longer in the Lagrangian, is that your potential is now going to be divided by this factor omega to the fourth. And omega, it comes from redefining the fields. It's defined on here in the middle of the page, the first of the three equations. You see that it's proportional to 5. So the price for this redefinition of the field is simply that now your potential is going to be divided by a quartic polynomial. But the simplest potential that we could have chosen in the first place was also a polynomial. So the ratio would be the ratio of two polynomials. So you see that the new potential, which is a function of h, which is the new field that occurs after you redefine the fields in the Lagrangian, is now a quotient of two quartic polynomials. And this is going to give us what we want, because as long as the parameters satisfy a certain relationship among themselves, we're going to get an inflection point in the potential. This inflection point is shown on the blue curve here, the blue dash curve. This is what I'm plotting. This corresponds to the potential, and the horizontal axis here is simply the field value normalized to m Planck. So you see that when h is around 1 m Planck, this blue curve, the potential has an inflection point. So around 1 m Planck is where we're going to produce these black holes. The red curve here is simply the speed of the field, and you see that it goes to 0 when the field is near the inflection point, which is what is going to give us the enhancement of the power spectrum. So something you might wonder is whether we actually needed to do this field redefinition to get the inflection point, because on the numerator we already have a polynomial that could have an inflection point if we choose A2, 3, and 4 correctly. So what the denominator is actually doing is that at large field values, it makes the potential constant. So you see that the blue curve at large field values, as h becomes bigger, it tends to a constant. Yeah, it's tending to a plateau. And this is going to help a lot when fitting the CMB data. So the reason that we need to include this denominator is that it makes it easier for us to fit the CMB data at large field values. So the intuitive idea that I gave you before, where the power spectrum was simply 1 over the speed of the inflaton, is actually not entirely correct. This is only validating what is known as the slow roll approximation. And it turns out that when the field is rolling very, very slowly, we actually break the slow roll approximation, and we are in a regime known as ultra slow roll. And this picture where the power spectrum goes as simply as 1 over the speed of the inflaton is actually broken. So to be able to compute the power spectrum, what you need to do now is to take this differential equation that's shown at the top here. It's known as the Mukhanov-Sasaki equation, and solve it numerically, usually numerically. And the power spectrum can then be obtained simply by squaring the solution that you obtain here. This equation is obtained simply by considering perturbation theory. So on the plot that I have on the left here, you can see the result that we would obtain for the power spectrum if we follow if we use the slow roll approximation in the red curve, and by solving this differential equation in the black curve. So you see that after the slow roll phase ends, so near the end of the plot, where you are in ultra slow roll, one is actually underestimating the power spectrum if one uses a slow roll approximation by many orders of magnitude. So it is important to solve this equation numerically to get an accurate power spectrum. The main issue that we run into with this polynomial model is actually adjusting the tilt of the power spectrum at CMB scales, which is also known as a spectral index. So the spectral index is simply the slope of the power spectrum at a given scale. And the problem that we run into is that trying to adjust the spectral index, we run into problems with the bounds coming from the Hawking radiation of the black holes. So let me elaborate on this. If you try to okay, let me first say that the spectral index that we get from this polynomial model is about 0.95, but the spectral index that we measure measured by Planck, for instance, in CMB experiments, is 0.965. This is a measurement that is done by assuming only lambda CDM. So you see that there is a bit of difference, and the problem is that if we want to increase the spectral index, if we want to fit the tilt of the power spectrum better at CMB scales, what we have to do is we have to change the starting position of the inflaton in the potential. But if we do this, then we're also going to be shifting the position of the peak in the power spectrum. And if we change the position of the peak, then we're changing the masses of the black holes. So this is why trying to adjust the spectral index at CMB scales results in a problem with adjusting the masses of the black holes, and we run into problems with the evaporation bounds. So there are two possible solutions to this problem, both of which are well motivated. The first one is we can actually extend lambda CDM by adding very reasonable extensions, like the neutrino masses, or adding the effective number of relativistic degrees of freedom, or just allowing the spectral index to run. And if you add these things to lambda CDM, Planck has already, the Planck collaboration has already performed this analysis, and what you find is that the new spectral index is about 0.95, which is very close to what we find. So this is one possible solution to the problem, just extending lambda CDM. Another solution, if you want to leave lambda CDM as it is and you don't want to add these things, is to add higher dimensional operators to the potential. These higher dimensional operators are expected anyway, because you're dealing with a model that is non-renormalizable, right? Because the inflaton is coupled to the Ricci scalar. So if you add these higher dimensional operators, then what's going to happen is that they're going to change the potential at very large field values, and then you're going to be able to fit the CMB data better. And at low field values, which is where the inflection point is, and it's where you produce the black holes, the potential is going to be basically the same, because these terms are not going to have an effect there. So the effect of these terms is to change the potential at the CMB, but leave it the same at the inflection point. And because the potential changes at the CMB scales, if you add these terms, then you're going to have a few more parameters that you can fit, that you can use to fit the CMB data. So this also solves, this increases the spectral index, solving the problem. On the left plot on this page, what I'm plotting is the abundance of these black holes, once again, in the vertical axis, and in the horizontal axis, the masses of the black holes. So there are, you can see in the colored regions with black lines going across are the experimental constraints that I showed you before. So the red one is the one from Hawking radiation, and the orange one is the one coming from microlensing experiments. And the two curves here, the green one and the blue one, are the solutions that I have just mentioned. So the green one corresponds to simply using a fourth order polynomial and extending lambda CDM. And the blue one corresponds to adding higher dimensional operators to the potential. So you see that with both of them, we can get a fraction of dark matter in the form of black holes of 1. So we can basically explain all of dark matter with black holes. Something important about this, and that is actually not just for this model, but this is a generic feature of all of these models of inflection point inflation, is that we get a very large gravitational wave signal. And the reason is that it's important to emphasize that this signal is not coming from the mergers of the black holes or anything like this. It's actually due only to the large power spectrum that we have. Because if you expand Einstein's equations to second order and you look at the equation of motion of the tensor modes, which are the ones that correspond to gravitational waves, at first order these are unsourced by any other perturbation. Yeah, they're by themselves. But if you expand the equations to second order, what you're going to get is that the second order tensor modes are now going to be sourced by first order scalars squared. And because we have a very large power spectrum, we have a peak in these scalar perturbations. And then this is going to lead, this equation of motion is going to lead to a peak in the second order tensor modes. And you can calculate this peak, and it turns out that for the black holes that we're interested in, it falls exactly in the frequency range that LISAR and the SIGO are going to measure. So this is something that this is a model that could be probed within the next 10 or 20 years once these experiments are active. So the next thing I want to tell you about is the formalism of stochastic inflation. In stochastic inflation, what happens is that we allow quantum fluctuations of the field to back react on the classical trajectory. And these quantum fluctuations are then going to modify the background evolution of the field. So the equation of motion that we have for the field in slow roll is what is shown here in this gray box. So the first term, the one involving the derivative of the potential, is the one that you would obtain if you were not considering the back reaction of the quantum fluctuations. Yeah. So if you're in slow roll and you do not consider the back reaction, what you would obtain is simply that the derivative of phi is equal to this first term. Yeah, the derivative of the potential. Then if you consider the quantum fluctuations, what you obtain is a second term. And the second term, you can think of it as a stochastic noise term. So at every point in time, this term psi, which is a stochastic noise, is going to give a kick to the inflaton. So this is why it modifies the background trajectory of a field. And then if you want to check how big this effect is, you want to check whether or not it has an effect. What you can do, because this is psi is basically just a probability distribution of the noise, so it's a number between 0 and 1. What you can do is you can divide the coefficients of both terms to see and check whether the result is bigger or smaller than 1, yeah, to estimate whether or not it has an effect. Then if you do this, what you find is that for the stochastic noise to not have any effect on the trajectory, the condition that you have to satisfy is that the power spectrum has to be much smaller than 1. This is actually an equation that is only valid in slow roll. And as I told you before, we actually have to break slow roll. So this is not a very good estimation, but it's enough to understand intuitively what's happening. So for the power spectrum that we measure at the CMB, which is around 10 to the minus 9 or so, this doesn't matter. You don't have to take into account the stochastic noise because 10 to the minus 9 is much smaller than 1. But because now we are enhancing the power spectrum in order to produce the black holes, and the power spectrum that we need is of order 10 to the minus 2. So it is a lot closer to 1. And then it becomes important to understand whether or not this has an effect. So this is the intuitive idea. And what you do to take into account these quantum fluctuations operationally is that you take the field, the inflaton field, and then you split it into a coarse-grained part and a perturbation. So the first term in this equation, this phi bar, it represents the coarse-grained field, and the second term represents the perturbation. You can see that the perturbation is actually multiplied by this function W. This is a window function that basically it separates small scales from large scales. So this K sigma is a cutoff that is going to, this cutoff is going to tell you which ones of the scales are classical and super horizon, and which of the scales are quantum and sub horizon. Then what you can do once you have this splitting of the coarse grained field and the perturbation is you can plug it back into the equations of motion, and you're going to find that the fields now satisfy what are known as the Langevin equations, which are the two that are shown at the bottom. And these are the equations for the field and its conjugate momentum, and each one has its own stochastic noise term. And these are the equations that you have to solve, basically. Now, solving these equations numerically is very difficult, so what we're going to do is we're going to develop an analytical formalism that is going to allow us to estimate the effect of this stochastic noise. So because we have quantized the perturbation, in principle, you have to think of the perturbation and the noise as operators, but it turns out that the commutator of the noise and the perturbations actually vanishes on small scales. And then instead of thinking of them as quantum operators, you can think of them as classical stochastic variables. So they're classical because the commutator vanishes. But even though they're classical, you cannot think of them as a single number because they are probability distributions. So you have to think about them as stochastic variables, even though they're classical. And it turns out that if we choose a window function that is a Heaviside step function, so yeah, this is the simplest possible window function that we could choose, just a Heaviside. What we obtain is that the noise that is generated is then Gaussian, which simplifies the equations a lot. So this is the window function has to be chosen by hand. This is not something that comes directly from the model. Yeah, you have to choose by hand what you consider classical and what you consider quantum modes. And if you choose a Heaviside step function, then you find that the noise is Gaussian. And now, because the perturbations are stochastic variables, their evolution is described simply, or their properties, if you want, are described by their statistical moments. Yeah, so they're going to be described now by their endpoint functions. In particular, we're interested in the 2-point functions, which you can compute by solving this set of 3 coupled differential equations. And you see that each one of these equations is sourced by this term d, which is the one that is related to the noise, because d is defined as this linear combination of thetas, and these thetas are precisely the correlation functions of the stochastic noise. So once you solve these differential equations, if you manage to solve them and you find the 2-point functions of the statistical moments of the perturbations, then you can find the power spectrum, because you can show that the power spectrum is given by the sum of these 3 terms. So the first term, this d phi phi, the one that is shown in black here, is what you would obtain if the perturbation, if you were not considering the stochastic formalism. So this is the result that I was showing you before, is the one that is obtained simply by considering this first term. These 2 terms that are shown in red are the additional contributions from the stochastic formalism. So what we want to check is whether or not these 2 terms, the sum of these 2 terms vanishes. And if we find that it vanishes, then what we're going to get is that the power spectrum is the same that we had before and is not affected by the stochastic formalism. So the way that we're going to do this is by developing an analytical model that is going to allow us to calculate explicit expressions for the stochastic noise. So this is a model that is actually quite generic, and that all of the models of inflection point inflation that produce primordial black holes behave in more or less the same way. So the model that we're going to develop here is quite generic for all of the models of this type. The model that we develop is a 3-region model. So, and it's illustrated on the plot that's shown on the left here. And what I'm plotting here is the second slow roll parameter, eta. And basically what eta is a parameter that controls the acceleration of the inflaton as it rolls down the potential. So in the beginning, at early times, eta is 0 because the field is in slow roll. So the slow roll parameter has to be small. So we simply consider it to be 0. And then eventually eta grows to a very large value, so bigger than 3 of order 1. And at the end of the model, at the end of the trajectory of the inflaton, eta decreases back to a negative value. So the blue curve that I'm showing here, the blue dash curve, is what you would obtain for eta in a numerical model. Yeah. So for instance, think about the polynomial model that I showed you before. Eta is what you would obtain if you were considering the actual numerical evolution of the inflaton. So the simplest way that we can model this evolution is simply by fitting eta with 3 Heaviside functions, one after each other. Despite the fact that this is a very crude approximation, it turns out that it actually reproduces quite well the results of the model. So by having the simple parameterization of eta, we can actually reconstruct everything that we need. We can reconstruct the potential, the trajectory of the inflaton, the first low roll parameter, and most importantly, the power spectrum. And because the parameterization is so simple, it's simply a constant eta in 3 different regions, solving the Mukhanov-Sasaki equation analytically is very easy. So the biggest advantage that we find with this approach is that now we can find explicit analytical expressions for the noise. So the expressions that we find for theta, remember, is the correlation function of the stochastic noise. The results that we find are shown in this table, and the actual values, the actual expressions are not that important right now. What's important is the fact that by developing this analytical model, we're able to find explicit expressions for the noise. And it turns out you can show that then by using this expression for the noise, you can solve for the statistical moments of the perturbations, and you can show that the 2 additional terms that appear in the power spectrum due to this new formalism actually vanish. So what we find basically is that this stochastic formalism does not have an effect on the power spectrum. So it's the same thing I told you before. So the power spectrum is the sum of these 3 terms, and the sum of the second 2 vanishes, as we can show analytically, and then the power spectrum is only given by the first term, which is what you would obtain if you were doing the calculation classically. What's important is that this vanishes only in the sigma going to 0 limit. So let me show you once again the cutoff here. So if you remember, the field is defined is split into a coarse-grained part and the perturbation, and what you consider classical versus what you consider quantum modes is basically determined by the cutoff that you choose here inside the window function. And the cutoff that we choose is simply sigma times a times h, because you can show that if sigma is small enough, then this cutoff accurately separates the quantum modes from the classical ones. So what we're plotting here is, what's important here is that you're only going to be able to separate the modes accurately if you choose sigma to be small enough. So if you don't choose sigma to be small enough, then you're going to get a different power spectrum, but this is only because you haven't chosen the cutoff correctly. So on the right side, you can see the cutoff for different values of sigma, which are these red lines. And the black line basically tells you when the modes become, when the quantum modes become classical. So you see that, for instance, if you choose sigma equal to 10 to the minus 2, then as long as the field is in slow roll, this is a good choice. But once the field is once you have an ultra slow roll phase, the modes take a little bit longer to become classical, which is why this black line has this nasty dependence on the number of e-folds. So if you basically what you want is for the entirety of the black line to be above the red line that you're choosing. So in this example, the minimum sigma that you would need to choose to accurately separate the quantum modes from the classical ones is 10 to the minus 6. And you see indeed that the power spectrum, which is shown on the left, that is obtained by choosing each value of sigma, which are the spectra shown in red, tends to the green curve as sigma becomes smaller and smaller. And the reason is that the green curve is the correct result, which is the one that you would obtain classically. So the stochastic inflation formalism does not have an effect on the power spectrum as long as you choose the cutoff correctly. The last thing that I want to tell you about is what happens if the black holes collapse during a matter-dominated era instead of a radiation-dominated era. So the one that we have been considering so far is the collapse of black holes during a radiation era. And if they form during an early matter-dominated era, then we actually need to estimate again the masses and the abundances of black holes. So as I showed you way back in the beginning, the mass of the black holes, if they're produced during a radiation era, is proportional to k to the -2, where k is the scale of the fluctuation. And we can compute the mass if they form during an early matter-dominated era. And what we find is that now they are inversely proportional to the third power of k. And this is not very important. It's almost the same dependence as before, but what is important now is that the mass is also proportional to the temperature at which the transition between this early matter-dominated era and the radiation era occurs. Similarly, you can do the same calculation for the abundance, and what you find is that if the black holes form during a radiation era, then you remember that it was proportional to this function beta, which was the amount of energy density that collapses into black holes. This is what is shown here as beta RD. And you would not expect the amount of energy density that collapses into black holes to be the same if the universe is dominated by radiation than if it's dominated by matter. Then you would expect it to change, and this is what is indeed what happens. So if the abundance for the black holes in a matter-dominated era is now going to be proportional to a different beta function, which we denote by beta MD, and once again we find that it depends on the temperature at which the transition between matter and radiation occurs. So these are the two key points. The first is that these expressions now depend on the transition temperature. And the second is that the fraction of collapsing energy density is given by a different function. So as I said before, beta is the fraction of energy density that collapses into black holes. And the dependence of this function on the power spectrum is very different depending on which era the black holes form in. So the radiation function is the first one that is shown in between these two equations in the middle. You can obtain this function by considering the Presch-Schechter formalism and postulating that a given density fluctuation only collapses as long as it is above some critical threshold, which is why this integral grows from some threshold delta c to infinity. And this is assuming that the probability distribution for this delta function is Gaussian. On the other hand, if these black holes form during a matter-dominated era, what you find is the second function here. And this function was found in these papers that are cited here. And this function takes into account the non-sphericity and the angular momentum of the collapsing cloud. So if you were to estimate naively if you were to think about, without doing any math, to think about what would happen if the black holes formed during a matter-dominated era, what you would expect is that the collapse is a lot easier because now there is no radiation pressure that is opposing the collapse. And indeed, if you were to use the first formula and simply take the limit of the equation of state going to 0, what you would find is that all of the matter in the universe collapses into black holes because there is no radiation to stop it. But this is vastly overestimating what happens. What actually happens is that whether the cloud that is collapsing is spherical or not has an effect. And if it is spinning, then the angular momentum actually also inhibits the collapse. So even though the equation of state is 0, you need to be careful about the calculation. And if you take these effects into account, then you find that even though the collapse is easier than in radiation domination, not everything in the universe collapses into black holes. So collapse during this early matter domination has two very big advantages. The first one is that because of what I just said, because collapse is easier during matter domination, And the power spectrum that you need to produce, to explain all of dark matter in the form of black holes is actually smaller. So in the radiation case, it's about 10 to the minus 2 what you need, but in the matter case, you only need it to be around 10 to the minus 4. And the second significant advantage is that the abundance of the black holes, because beta is different, the abundance is now a lot less sensitive to small changes in the height of the power spectrum. So let me elaborate on these 2 points with these plots. In the plot that I show on the left side, what we have is in the vertical axis, we have the temperature, the transition temperature between matter and radiation. And in the horizontal axis, what we have are the scales of the fluctuations that are collapsing. So the 2 shaded regions, what they show is that the regions that are forbidden. The blue region is forbidden because for those choices of scale and transition temperature, the scale actually re-enters during radiation domination. So this is not what we want. What we want is for the scale to re-enter the horizon during matter domination, during this early matter dominated era. And then for that to happen, you have to be below the blue region. So yeah, the white region. On the right side of the plot, well, first let me tell you, the orange lines that are going across in vertically, or diagonally rather, are the masses of the black holes that you would produce for each one of these choices of temperature and scale. So you see that smaller masses are to the right side. And if you recall from the plot that I showed you ages ago, the smaller masses are constrained by the bounds coming from the Hawking radiation of the black holes. And this is what is shown in the red region. The red region corresponds to the Hawking radiation bounds. So it's which would correspond to small masses, and therefore it's also forbidden. So the region that is allowed is the one shown in this white triangle. And you can see that the best case scenario would occur on the top right of the triangle, which is where the power spectrum, which is given by this horizontal dashed line, is smallest. So in the best case scenario, the temperature that you would need to produce black holes to explain all of dark matter is around 10 to the 5 or 10 to the 6 GeV. So we're talking here about very low reheating temperatures, very low transition temperatures. So yeah, the key point here after all of that is simply that if you have an early matter-dominated era that ends when the universe has a temperature of 10 to the 5 or 10 to the 6 GeV, then you only need a power spectrum of 10 to the minus 4 to produce the black holes, which is an improvement over the radiation case. On the plot of the right side, what I'm showing is the sensitivity of the abundance to small changes in the height of the power spectrum. So the purple curve shows the sensitivity of the abundance if the black holes form during a radiation era, and the blue curve shows the sensitivity of the abundance if the black holes form during a matter era. So you see the important point here is that the blue region is a lot bigger than the purple region. And what I'm depicting here is a 1 order of magnitude change as I change the parameters inside the function. So you see that if I change the power spectrum by a little bit, just by a little bit in the horizontal axis, I already reach a 1 order of magnitude change in the purple, in the radiation case, which is why the purple region is so small. But to reach the same amount of change in the blue case, I have to change the power spectrum by a lot. So the point here is that it is the abundance is a lot less sensitive to small changes in the height of the power spectrum. And this is good because it means that you're going to have to tune the parameters in your model less to get the same amount of black holes. As a way of implementing this mechanism, you can consider this action monodromy inspired potential. And what this potential does is it features a bunch of oscillations because of the cosine term and this quadratic near the minimum. So why is this important? It's because once the inflaton reaches the minimum of the potential, what you have is you can show that if the minimum is quadratic enough, what you have is that the inflaton is when it oscillates around the minimum behaves as matter. So once inflation ends and the inflaton starts oscillating near the minimum of the potential, what you're going to have is a long epoch of matter domination. as long as preheating is perturbative, meaning that no preheating occurs. But this is going to depend, of course, on the coupling of the inflaton to the other particles in your model. So the original motivation that we had, well, let me first tell you about the parameters and the potential. This P parameter that is shown here controls the slope of the potential at large field values. So this P parameter basically is what is the main thing that is going to determine how well you're going to fit the CMB data, because it's what changes the potential at large field values. At low field values, as you can see in this plot, this P parameter doesn't really have an effect. And what does have an effect is this kappa parameter. This kappa, which is multiplying the cosine, changes the depth of each one of these minima. And this depth is what you want to change in order to obtain a large enhancement of the power spectrum. So basically, this kappa parameter is going to determine how big your power spectrum is, and the P parameter is going to determine how well you can fit the CMB data. So the last thing that I wanted to tell you here is that the motivation that we had to choose this potential was we thought maybe by having many oscillations in the potential, we could reduce the tuning in the parameters of the model. The reason being that it is if you have several minima, then maybe even if the inflaton does not produce the black holes in one of the minima, it would produce them once it reaches the next minimum. And it turns out that this is not the case, because the abundance is so sensitive to this to the depth of each one of these minima that you have basically just have to choose one of the minima and tune that to get the correct amount of black holes. So actually, you didn't need you don't need to use a potential this complicated to implement the matter-dominated scenario. As long as you can get an early matter-dominated error via some other mechanism, you can always, for instance, from the same polynomial model that we had before, you could also get the black holes. So nevertheless, we're going to choose this potential, and the mechanism is now illustrated in these examples that I show here. So on the left side, you can see the power spectra that we get for when all of the parameters in the potential are equal to between each example, except for kappa, which, as I said, is the parameter that controls the depth of each minima, and therefore is what controls the size of the power spectrum. And so the highest of these power spectra, which is around 10 to the minus 2, is what's going to correspond to producing these black holes during a radiation era, and the two smaller spectra correspond to producing these black holes during an early matter-dominated era. And the corresponding the abundances corresponding to each one of these three examples is shown on the right side. So once again, the power spectra that you need to produce them during radiation, you can see that it's a lot bigger than what you would need if you wanted to produce them in matter domination. So the different abundances are shown on the right side. And you can see that the abundance corresponding to the radiation case is actually a lot narrower than the one corresponding to the matter case. And the reason is that precisely because the beta function that determines the abundance is different, and because you don't have in the matter case, you don't have the exponential dependence that you had in the radiation case. This exponential dependence in the radiation case was actually giving you a suppression to this abundance. Now, because you lose that suppression, the distributions are a lot wider, and this is a problem because if they are too wide, then you can see that you run into problems with the bounds coming from Hawking radiation, which are shown in red. So one way to overcome this problem is to actually change the parameter I that is in the beta function and which is related to the angular momentum of the collapsing cloud. So let's go back quickly to the function. You see that in the second beta function, you have this parameter I, which is, as I said, is related to the angular momentum of the collapsing cloud. And this should be a parameter. If you estimate it, you find that it should be a parameter of order 1. So if you play around with this parameter, meaning that basically what you're doing is you're changing the angular momentum of the cloud that is collapsing, what you find is that you get a bit of additional suppression to the abundance, and the price that you have to pay, of course, is that the power spectrum now has to be a little bit bigger to account for this. But by changing this parameter a little bit, you can evade the evaporation bounds. So the conclusion here is that the main advantage of the matter-dominated scenario is also the biggest drawback, which is that lack of suppression makes it more difficult to evade the evaporation bounds. And with this, I conclude. So the first thing I want to say is that the simplest potential that can produce primordial black holes is still viable, provided that you either extend lambda. By the simplest potential, what I mean is the polynomial potential that I showed you at the beginning. It's viable provided you either extend lambda CDM or you add higher dimensional operators to the potential, and both of these are natural solutions. The second thing is that if dark matter is in the form of black holes, then we should be able to detect the corresponding gravitational wave signal with lights around the zygo if they form during radiation domination. The third thing is that we have shown analytically that at leading order, at least, the stochastic inflation formalism does not affect the power spectrum, even in the presence of an ultra-slow roll phase. It's important to note that this is only a leading order. This does not mean that the formalism of stochastic inflation does not have any effect on the abundance of the black holes. But at least with the approximations that we made, we find that it doesn't. You would have to solve the Langevin equations completely numerically to find the correct effect of the formalism. But within the approximations that we made, we find that it does not have an effect. The next thing is that the primordial black hole formation in an early matter-dominated era has two big advantages. One is that because of the lack of radiation pressure, you need a smaller enhancement of the power spectrum to produce the black holes. And the second one is that the parameters in your potential are now going to be less tuned, precisely because the beta function is different. Then it is a lot less sensitive to small changes in these parameters. And the final thing is that the drawback of this matter-dominated scenario is that this lack of suppression makes it a lot more difficult to evade evaporation bounds. And yeah, that is everything I wanted to talk to you about. So thank you very much, and thanks again for having me.
Thank you very much, Julian. So just before to start with the session round, you can, for the people that is following the YouTube channel, you can ask questions via the YouTube chat. So in the beginning, we are going to start with some questions from here from the audience of the lawphysics. So I guess Alejandro Cárdenas want to address a question for Julian.
Thank you, Roberto. And thank you, Julian, for this very interesting talk and well-presented talk with a lot of details. I'm not an expert on this, but I'm curious about the, for example, here, your second conclusion here about the detectability. So I believe what you show for this to address detectability is the gravitational wave energy density, which is like, it seems like you compute the perturbations and then you hit the noise curve to assess that it will be above the noise curve of LISA that's detected. But so my question is more about how actually this will be detectable, in the sense that it is, I believe that what we typically do is we compute gravitational waves and then we will do either match filtering or something to extract that signal.
Yes.
So could you please comment on these cosmological things? Like, do they actually have
so this, so this, what you're talking about, this match filtering, is actually what you would use if you were detecting, for instance, a burst.
Correct.
A burst of a signal, right? If you had a merger or something like this. But what I'm talking about here is actually a stochastic background. So you would not see a burst, but rather what you would find is that there is additional noise in the mirrors that you do not know how to account for. So it's basically the same thing that happened when we found the CMB. There was this additional noise that nobody knew where it was coming from, and it turns out that it's because of this stochastic radiation that's in the background. It's exactly the same here. So this would just show up as stochastic noise in the movement of the mirrors.
So do you know if there are any works related, like if this actually, for example, for LISA can be extracted, in the sense that LISA will have a lot of constant sources in this, like, I don't know, a wide dwarf population. So this is different, like in LIGO, for example, is more or less what you just mentioned, that you will have a burst and then you can detect it because you can fit this. But in LISA is different because all the sources are sort of turned on at the same time. So do you know, like, even though here, for example, it looks like it's way above the noise curve, it means that so it will be a detectable in that sense because you can really model this noise and then extract it.
Yeah, so what you're seeing here in this noise curve is precisely gives you that information, right? As long as you have a curve above this this curve, it means that you can account for the. So what the noise curve is showing you is every source of noise that we know about, and this is actually what is modeled when you draw this curve. So yeah, as long as you find anything that is not this curve, as long as you find anything that is above it, then you know that that this is a source of noise that you have not accounted for. And I guess once you rule out everything, like I don't know, astrophysical sources of noise, for instance, which is actually what is modeled in this curve. Well, the first thing that you would think is that it's a stochastic background, right?
Okay.
So
yeah,
so it's detectable as long as it is above this this noise curve.
Yes, but for example, if you think about I don't know, for example, the nominal or like the first gravitational wave detection with LIGO that could have been observed with LISA, but then you see that it just leaves the band and then goes to LIGO band, for example. But then even in those cases, I believe it's quite actually challenging, even though it's above the noise curve. There are, as I said, like a lot of other sources. So my question is, like, if somebody has actually performed an analysis saying like you can indeed model for white dwarfs and I don't know, supermassive black holes, EMBRIs, LIGO type sources that will be seen first at LIGO and in LISA, and then this stochastic background.
Yeah, so my understanding is that this noise curve actually already accounts for all of these different noise sources. I may be wrong, but my understanding is that this red curve, for instance, that I show here as LISA, is actually already has all of those noise sources into account. And I don't know if there maybe I'm wrong. I don't know, but this is my understanding.
Okay, thank you.
Okay, let's see if there are some questions for the people in YouTube if they want to ask to Julian. So meanwhile, we can start with some other questions here for the audience in the Zoom session. I don't know if
I have a question.
Nicolas want to ask.
Okay, thanks Julian for the nice talk. Could you please go back to your slide? I think it was 16, when you talked about the formation of PBH in the matter era. Yes, okay, first one question. Does Tm correspond to the reheating temperature, or did you say transition temperature? What's that exactly?
So the Tm, let me show you the plot I had before. So it's a plot with a different era. So you can see that Tm is the temperature that corresponds between to the change between the early matter dominated and the radiation era. So I call it reheating temperature sometimes because the easiest way that you can get an early matter dominated era is if you have perturbative reheating. So if the inflaton is oscillating around the minimum of the potential and reheating is perturbative, then this early matter dominated era comes from reheating. But the models that I'm showing you here are not dependent on that. So Tm is basically the transition temperature, regardless of whatever mechanism you use to get this early matter dominated era.
Okay, but yeah, but is the onset of the radiation, right? Radiation dominated era.
Yes.
Okay, I see. And thanks. And if you go back to that slide, so 16, so maybe it's my intuition that it's miserably failing, but you say that PBH only grows during radiation. I was expecting the opposite, right? I mean, in matter, there's no pressure, so expecting PBH to grow even faster than radiation.
No, so what what happens during matter era is that this is when they form. So you're correct that when they form, it's easier for them to form if they are in a matter era than if they're in a radiation era. But once they have formed, once you have already all of your black holes in the universe, because the black holes behave as matter, right? This is why we can think of them as dark matter. They behave as a matter fluid. Their energy density, the energy density of the total amount of black holes redshifts as the scale factor to the power -3, right? Because it's matter. But radiation redshifts as 8 to the -4. And so if you take the ratio, you find that radiation redshifts more quickly than the black holes, and this is why the total energy density actually grows during the radiation era. So if the universe was always matter dominated, for instance, you would not have a growth of the abundance, right? Because the ratio would be the same always. So this is why this is why it grows during radiation.
Okay, so you mean that the proportion of energy stored in PBH is growing?
Correctly,
Not that
yes.
that a single PBH is like accreting or something like this.
No.
I understand.
Exactly.
Okay, thanks.
Okay, maybe are there other questions for the moment? Just from YouTube, the RB Fair, he's saying that it was a very nice talk, that he thanks to you, Julian. So I don't know if there are other questions, but I have a very small question about if you can comment about DesiGo, because you, I mean, I didn't know that existed, so maybe it's my ignorance. If you can comment, because most of the capability of DesiGo was in the area in which your model is producing a lot of signal. So
yeah, so I don't know much about the experiment, so I can't say a lot. I don't know, so it's a little bit to the right in the frequency range. It's a little bit to the right of LISA, but there's some overlap between both, as you can see here. And I don't know what this is an experiment that is planned, yeah, and it's not something that's constructed yet, same as LISA. And well, there's not much more I can say. I think it's an experiment that we do not have yet, but yeah, it falls. It would, if it gets constructed, it would be good to probe this kind of model. So it's a sort of complementary to LISA in the same frequency range.
Okay, but just a naive question. So this DesiGo is ground-based?
No, I think it's. I think
space-based.
Maybe I'm wrong, but I think it's space-based as well, just like LISA.
Okay. Yeah. Okay. So another question, a very, I mean, also naive question, is when you were talking about the stochastic inflation, because it looks very similar, just not the physics behind, but just the formalism. It looks very similar to when people try to solve the stochastic differential equation. Is it inspired in the same?
Yeah, this is exactly the same. It's these are actually stochastic differential equations. So if you want to do them, if you want to solve them completely numerically, you know, to get a full solution, you have to use stochastic methods. So yeah, this is exactly what happens at each step in time. This thing gets a stochastic kick. So you have to solve them many times and build like a probability distribution of the solution. So yeah, they are stochastic equations.
Okay. So yeah, okay. Yeah, because when I looked at the formula, it looked very similar, because in other fields also they appear like in anything that where is randomness. Okay. Yeah, just that question. So I don't know if we have more questions from the audience. Okay, I guess Oscar Zapata wants to ask one question. Please, Oscar.
Okay, thank you for the nice presentation. I would like to Julian regarding the constraints, namely the vector lensing constraints. Could you comment something about them? And
yeah, so
I have heard that there is some I don't know tension in that kind of constraints.
So, well, the real constraints that we have come from microlensing, not from femtolensing. The femtolensing constraints are the ones that are shown in pink here, and this is not an actual constraint. This is just a projection of future constraints we could have from femtolensing. The microlensing constraints are actual constraints, and let me show. They are this curve that is around 10 to the minus 11 solar masses from the Subaru experiment. So I don't know the story about these constraints too well, but you're right. As you can see here, there is a very this is like a vertical line that is cutting these constraints below 10 to the minus 11, and I think that the tension that you were referring to is the fact that before this wasn't a vertical line, right? This was a full constraint that went to around the middle of this open window. But then I think what happened is that people realized there were some astrophysical uncertainties with these constraints, and then what happened was that they had to revisit the original estimation. They had to cut this side because of these astrophysical uncertainties. And then I think the actual constraints that we have now are more or less this. I don't know if there are some updated plots, but as far as I know, these are the ones. And they end at around 10 to the minus 11. There's this sharp cut here precisely because of the uncertainties that were not taken into account before. I don't know if that answers the question.
Yes, thank
you. Okay, I don't know, maybe if there is another question for Julian. Just check fast in the. Okay, it seems that we are okay, and also due to time we have to close here. So let's invite everybody to thanks to Julian for his very interesting talk. Indeed, was very. I mean, I learned a lot with his talk. So for the rest of the people, you know that you can follow the lawphysics YouTube channel. You can subscribe to be updated with all the latest webinars that we are programming during the year. It's 2021. So, and for the next webinar is going to be around 2 weeks more. It's going to be webinar 109, and it's going to be Christoph Termes from University of Torino. So he will talk about neutrino oscillations, more or less. That is going to be the topic. So I invite everybody to join for the next webinar, lawphysics webinar, and see you next time. Thanks, Julian, again for your nice webinar.
Thank you very much for having me.
And we see each other next time here in lawphysics. Bye.